Here we have the limit as x goes to infinity of 1 plus 2 over x, the quantity, to the x. The denominator is going to infinity if I'm looking at this term, and the numerator is fixed. That's going to go to 0, and then I would have 1 to the infinity. But what is 1 to the infinity? It's not a number. Infinity is a concept, and is it stay 1 or does it do something else because it's going to infinity? So we are going to learn how to deal with this one, and what we're going to want to do, we can't deal with that x up in the exponent, so we're going to do something that we did before when we were trying to find derivatives and there was an x and an exponent, taking the natural log so that we can move it out in front. But right now it's not an equation so that I could take the natural log of both sides, so I'm going to make it an equation. I'm just going to write L for limit equals the limit as x goes to infinity of 1 plus 2 over x to the x. Now I'm going to take the natural log of both sides, and when you have a limit you can take the natural log inside the limit, so I'm going to put it in there because once I have the natural log of this stuff raised to the x power, I can use the third property of logs that says I can multiply that power out in front. So this is going to become the limit as x goes to infinity of x times the natural log of 1 plus 2 over x. Okay, now as we're looking at this, what I've just written down there in green, I'm seeing that if I tried to look now, I would have an infinity right here, and then I'd have the natural log of 1, which is 0, so I've got an infinity times 0. I can't use L'Hopital's rule in that form, but I can take this x and I can flip it over. It's like x over 1. If I flip that over and brought it down here, that's equivalent. And now if I looked as x goes to infinity, I'd have the natural log of 1, which is 0, and in the denominator I would have a fixed numerator, denominator becoming huge, which would go to 0. So I would have a 0 over 0. So I can now use L'Hopital's rule. So I'm going to put it down here, and I'm going to put an H because I'm using L'Hopital's rule to get this. So I have the limit as x goes to infinity. I need to take the derivative of the top. Natural log would be 1 over what's inside the natural log, but then the chain rule applies. We need to multiply by the derivative of what was inside that natural log, and the derivative of 1 is 0, but the derivative of 2 over x is going to be negative 2 over x squared. And that's just on top because it's multiplied by the 1, so I don't need to write the 1 anymore. And now what was I doing? I was doing the rule which says taking the derivative of the top, and all of that was the derivative of the top, and then taking the derivative of the bottom, it's negative 1 over x squared, because think of this like x to the minus 1. You do the power out in front, decrease the power by 1 makes it x to the negative 2, and then I brought it down to the bottom to not have a negative exponent. Okay, so now I'm going to see what I can do to simplify this. I can take this bottom and I can flip it over and multiply it. And when I do that, then I see a couple things cancel. Negative times a negative will be positive, and this x squared and this x squared will cancel. So let's rewrite what we've got. We've got the limit as x goes to infinity of, looks like that's just going to be a 2 over 1 plus 2 over x. And hey, that's something I can find now, because as we let x go to infinity, 2 over something going to infinity, that part's going to go to 0. So it looks like my final answer is 2. But wait, what was the 2? All of this we were doing was equals, 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 but we started with natural log of L. So I'm going to rewrite that. We have natural log of L equal to, remember L stood for the limit, and we're trying to find the limit, so let's get rid of the natural log by exponentiating both sides. The e and the ln undo each other, and the limit of this then equals e squared.